Hey guys, there is a question so old, so stubborn, and so gloriously resistant to easy answers that philosophers were wrestling with it more than 16 centuries before modern physics even existed. The 4th century theologian Augustine of Hippo sat down, opened his notebooks, and genuinely tried to work out what God was doing before the creation of the universe. He was not the first to ask. The question had been circling around philosophical thought since the ancient Greeks, but his answer was striking for its intellectual honesty. Augustine argued that time itself was a feature of creation, not something that pre-existed it, which meant that asking what came before was structurally incoherent. The question carries its own contradiction baked right in. Before implies time. Time implied creation. Therefore there was no before. 16 centuries later, we have particle accelerators capable of recreating conditions microseconds after the Big Bang. We have space telescopes that can peer back to when the universe was less than 1 billion years old. We have gravitational wave detectors that can hear the collision of black holes 1 billion light-years away. We have computers that can simulate the curvature of space-time in extreme environments. We have mapped the oldest light in the universe with staggering, almost absurd precision. We know its temperature to 3 decimal places. We have charted its fluctuations across the entire sky to better than 1 part in 100,000. And we are still wrestling with essentially the same question Augustine was wrestling with. Not because science has failed us, but because this particular question sits right at the razor-sharp edge of what physics can even describe. The frontier between what is known and what may be, in principle or in practice, unknowable. What was here before the Big Bang? Spend 30 seconds really sitting with that. Not just nodding along, actually try to picture it. Everything you can see with your naked eye on the clearest night, every star, every smudge of the Milky Way, every galaxy the Hubble Space Telescope has ever photographed. All of it, all the matter and energy and space-time that makes up the observable universe, once compressed into a space smaller than a single proton, a fraction of a second after the beginning. And before that moment, before that impossibly hot, impossibly dense origin, what? More space? Another universe? Nothing at all? Something we don't have words for yet? Something the word something doesn't even apply to? The reason this question is so uniquely disorienting is that it pushes against something very fundamental in how human minds are built. We live embedded in causality. Every single experience you have ever had was preceded by something that caused it. You woke up this morning because you went to sleep last night. You went to sleep last night because you were tired, and you were tired because of everything that happened during your day, and your day happened because of all the days before it, stretching back through your childhood, your birth, your parents' lives, back through history and evolution and geological time and cosmic history to the very beginning. This cause and effect structure, this chain of events where everything has a prior cause, is so deeply woven into how human minds work that imagining its absence doesn't just feel counterintuitive, it feels almost physically impossible, like trying to imagine a new primary colour or imagine what lies beyond the boundary of space. And yet here we are, genuinely asking it. Because here's the thing, modern physics hasn't shut this question down, far from it. If anything, the intersection of quantum mechanics, general relativity, and 21st century theoretical physics has blown the question wide open in ways that would have been unimaginable even 50 years ago. Where a simpler era of science might have simply said, the universe began, full stop, end of discussion, the question is malformed, we now have a whole toolkit of mathematically rigorous, scientifically serious ideas that suggest there is indeed a story to tell about what came before, the moment we used to think of as the beginning. So that is exactly what we're going to do tonight. We're going to work through the full landscape of ideas, the theoretical frameworks, the observational evidence, the hard limits of what science can know, the philosophical depths beneath, the physical questions, and we're going to confront this question with every tool currently available to physics and to thought. Before we begin, I want to be honest with you about something. By the end of this video, you are not going to have a definitive answer. Nobody does. If anyone tells you they do, they are either simplifying to the point of distortion, or they are not being straight with you. What you're going to have is a genuine, nuanced, detailed understanding of why this question is so profound, which specific theories physicists find most compelling, and why, what the mathematical logic behind each theory actually is, what observational evidence we have, and what we hope to get, and where the true frontier of human knowledge currently sits. And that, I would argue, is much more interesting than a simple answer. Let's begin at the beginning. Or rather, let's begin just before the beginning. Before we can talk intelligently about what came before the Big Bang, we need to be extremely precise about what the Big Bang actually was. Because most people carry a mental picture of it that is, in important ways, wrong, and that wrongness matters enormously when you're trying to reason about what might have preceded it. Getting the Big Bang right is not just a warm-up exercise. It is foundational to everything that follows. First, and most importantly, the Big Bang was not an explosion in the conventional sense. When most people hear the word bang, they imagine something like a tremendous explosion, a central point of origin, matter and energy flying outward through a pre-existing space, the way debris flies outward from a bomb. That picture is fundamentally incorrect, and the incorrectness is not a minor quibble. The Big Bang was not matter and energy flying outward through space. It was space itself expanding, taking everything within it along for the ride. There was no center of the Big Bang from which everything expanded. Every point in the universe was simultaneously the site of the Big Bang, and there was no outside the Big Bang, no pre-existing space into which the universe expanded, no vantage point from which you could have watched it happen. This is genuinely hard to visualize, and there's a reason for that. Our intuitions are built for the scales at which we live, and the Big Bang operates at scales that our intuition simply weren't built to handle. The best analogy, imperfect like all analogies but useful, is a raisin bread. Imagine the bread dough rising in an oven. The raisins embedded in the dough move apart from each other as the dough rises, not because the raisins are moving through the dough, but because the dough between them is expanding. An ant standing on any one raisin would see all the other raisins moving away from it, and the more distant a raisin, the faster it would appear to recede. The ant might conclude it's at the center of the expansion, but every raisin would reach the same conclusion, because every point in the expanding dough is simultaneously the site of the expansion. There is no center, there is no edge. The universe is like that, but in 3 dimensions rather than 2, and without an outside you could view it from. What do we know observationally about the Big Bang and the early universe? Quite a lot, and it's extraordinary stuff. The absolute cornerstone of our knowledge is the cosmic microwave background, abbreviated CMB. This is the oldest electromagnetic radiation in the observable universe, and understanding what it is and what it tells us is essential context for everything we'll discuss tonight. For the first 380,000 years after the Big Bang, the universe was filled with a plasma, a hot, dense fog of protons, electrons, neutrons, photons, and other particles, all jostling together in conditions of extreme temperature and density. This plasma was so dense that light could not travel through it freely. A photon would be absorbed and re-emitted almost immediately, bouncing around like light in a fog. The universe was completely opaque. Then, approximately 380,000 years in, something happened that cosmologists call recombination, though it's something of a misnomer, since the particles were combining for the first time, not recombining. As the universe expanded and cooled, it reached a temperature at which electrons could stably combine with protons to form neutral hydrogen atoms. This happened throughout the entire universe almost, simultaneously, and when it did, the universe became transparent. Photons were suddenly free to travel, and they flooded outward in every direction. That ancient flood of light is still travelling today. Over 13.8 billion years, the expansion of the universe has stretched those photons, originally in the infrared and visible range, all the way down to the microwave range, arriving at our instruments from every direction, simultaneously at a temperature of just 2.725 degrees above absolute zero. This is the cosmic microwave background. NASA's COBE satellite first mapped its fluctuations in detail in 1992, earning its lead researchers Smoot and Mather a Nobel Prize in Physics in 2006. The Wilkinson Microwave Anisotropy Probe, or WMAP, followed with dramatically higher resolution in the 2000s. And then the European Space Agency's Planck Observatory produced the sharpest map of all, confirming the Big Bang model in extraordinary quantitative detail. The exact ratio of hydrogen to helium produced in the first few minutes, the spectrum of fluctuations that seeded all the galaxies and large-scale structure we see today, the geometry of the universe to exquisite precision. those temperature fluctuations in the CMB are worth dwelling on for a moment, because they're genuinely astonishing. The CMB is uniform to about 1 part in 100,000. That means you can look in any 2 directions in the sky, literally any 2 directions, and the CMB temperature differs by less than a fraction of a tenth of a percent. The universe was extraordinarily smooth and homogeneous when the CMB was emitted. The slight variations that do exist, those 1 in 100,000 ripples, are the imprints of quantum fluctuations in the very early universe, stretched and amplified by the expansion. Every galaxy you have ever seen in a photograph of deep space, every spiral galaxy, every elliptical, every galaxy cluster, every filament of the cosmic web, traces its origin to one of those tiny temperature ripples in the CMB. The largest structures in the observable universe were born from quantum fluctuations. What else do we know about the universe? We know it is expanding, and that the expansion is accelerating, driven by something we call dark energy, a form of energy intrinsic to empty space that makes up about 68% of the total energy content of the universe. We know the universe is geometrically flat, or at least flat to within the precision of our measurements, which means its total energy density is very close to a critical value. We know it is homogeneous and isotropic on the larger scales, looking the same in every direction and from every vantage point. And we know it is about 5% ordinary matter, 27% dark matter, which we can infer from its gravitational effects, but whose fundamental nature remains unknown, and 68% dark energy. We can trace the history of the universe back through billions of years of cosmic evolution with high confidence. We have detailed observational data on when galaxies formed, when the first stars lit up, how the large-scale structure of the cosmic web assembled. We have theoretical models confirmed by observation of the formation of light elements in the first few minutes of cosmic history, a process called Big Bang nucleosynthesis. The predicted abundances of hydrogen, helium, deuterium, and lithium match observations to impressive precision. This is one of the strongest confirmations of the Big Bang model. But here's where the story gets complicated and the real conversation tonight begins. As we trace backward in time toward the very beginning, toward higher and higher densities and temperatures, we eventually reach a barrier. Not a physical barrier, an intellectual and mathematical one. At a moment known as the Planck time, approximately 10 to the power of negative 43 seconds after the Big Bang, a number so small that writing it out as a decimal would give you a string of 42 zeros followed by a 1. Our equations stop working. Not because we've done anything wrong, not because of a computational error, but because at the densities and temperatures prevailing before the Planck time, quantum mechanical effects on the fabric of spacetime itself become dominant, and we do not have a consistent mathematical theory that handles both quantum mechanics and gravity in this extreme limit. General relativity, Einstein's masterwork, our best theory of gravity and the large-scale structure of spacetime, predicts a singularity at the Big Bang, a point of infinite density and infinite temperature, where the mathematical curvature of spacetime becomes infinite, where the equations spit out nonsensical values, where the theory has broken down completely. In physics, when your equations give you an infinity where the universe gives you something finite, that's always the signal that you've pushed a theory beyond its range of validity, that you need something better. And almost every theoretical physicist alive believes that is exactly what has happened. The Big Bang singularity is almost certainly not a real physical object. It is an artifact, the screaming protest of a theory being applied to conditions it was not designed for. Just as Newtonian mechanics gives nonsensical answers when applied to particles moving close to the speed of light and is replaced by special relativity, general relativity gives nonsensical answers when applied to densities so extreme that quantum gravity effects dominate. The problem is that we don't have a working theory of quantum gravity. We have candidates, loop quantum gravity and string theory are the most developed, but neither has been fully worked out or definitively tested. This is the central unsolved problem of theoretical physics, and has been for most of the last century. Until it's solved, any description of what happened at the Big Bang itself, and a fortiori any description of what came before, is necessarily theoretical, necessarily incomplete, and necessarily subject to revision. The Big Bang then is not really the beginning of the universe in an absolute sense. It is the beginning of the universe as we can currently describe it using the physics we currently have. It is the edge of our map. And as anyone who has studied the history of exploration knows, the edge of the map is precisely where the most interesting discoveries happen. Here is the most mind-bending idea in this entire conversation, and the one that most people, including many science communicators, don't spend enough time with. It is not just physically uncertain what came before the Big Bang. It may be conceptually incoherent to even ask the question in the way we normally ask it. The word before implies time. It implies a sequence of moments. First A, then B. A is before B. This is so deeply embedded in how we think that we rarely notice we're doing it. But physics has been telling us for over a century that time is not what we intuitively think it is. In 1905, Einstein's special theory of relativity demolished the notion that time is absolute, that there is a universal now that all observers agree on. Two observers moving relative to each other will disagree about the timing of events, and under some circumstances will even disagree about which of two events happened first. Time is not a fixed universal backdrop against which events unfold. It is part of the physical measurement process itself, dependent on the state of motion of the observer. In 1915, Einstein's general theory of relativity went even further. It showed that time is not merely relative to the observer's motion, but that time itself is part of the physical fabric of space-time, a four-dimensional geometric structure that is curved and warped by the presence of matter and energy. Near a massive object, time runs more slowly. This is not a hypothetical. It is measured daily by the GPS satellites overhead, which run slightly fast relative to clocks on Earth's surface, because they're farther from Earth's gravity, and must be corrected for, or your GPS would accumulate errors of several kilometers per day. Now take this idea, that time is a physical quantity, part of the geometry of space-time curved and shaped by matter and energy, and follow it all the way back to the Big Bang. If space-time is what the Big Bang created or expanded, if space and time themselves were part of the cosmic expansion, then asking what was before the Big Bang is asking about a time that did not yet exist. It's like asking what's south of the South Pole. You're trying to apply the concept of before to a situation where before has no referent, no time in which it could be before. Stephen Hawking spent much of his later career explaining this idea to the public, often using the South Pole analogy. In one of his final lectures, he said it directly: events before the Big Bang are simply not defined, because there's no way one could measure what happened at them. Since events before the Big Bang have no observational consequences, one may as well cut them out of the theory and say that time began at the Big Bang. The question of what happened before the Big Bang is like asking what's north of the North Pole. It doesn't make sense to expect an answer because the concept being applied doesn't apply there. Hawking and James Hartley formalized this intuition in their famous no-boundary proposal, first published in 1983. The no-boundary proposal is a specific mathematical model of the quantum state of the universe, a way of describing the universe's wave function, using a technique called the Euclidean path integral. In this approach, one performs a mathematical trick. Instead of treating time as a real number, you treat it as an imaginary number, in the mathematical sense, multiplied by the square root of -1. When you do this, time and space become mathematically equivalent, and the distinction between before and after dissolves. In this imaginary time, the beginning of the universe looks not like a sharp point or an edge, but like a smooth, round surface, like the South Pole of a sphere. You can travel in any direction from the South Pole without hitting a boundary. The surface just curves away in all directions. Similarly, the beginning of time in imaginary time has no boundary, no edge, no before. This is genuinely extraordinary mathematics, and the physical interpretation it suggests is no less extraordinary. The universe is self-contained and self-explaining. It doesn't need anything to come before it, because before doesn't exist in the relevant sense. The universe simply is, complete and without a prior cause in the temporal sense, because time itself is one of the universe's features. This is a profound and intellectually powerful position, but, and this is crucial, not everyone in physics accepts it, and the reasons for not accepting it are not mere philosophical quibbles. They are substantive. The first problem is technical. When physicists try to compute the no-boundary proposal using the full rigorous machinery of quantum mechanics, specifically the Lorentzian path integral rather than the Euclidean one, they run into mathematical instabilities. The proposal tends to predict that the universe should be in one of many chaotic, fluctuating states, rather than the smooth, ordered state we actually observe. The specific smooth beginning that Hawking and Hartley's proposal was designed to explain turns out to be exponentially unlikely in certain rigorous formulations. Several recent papers, including work by Neil Turok, Job Feldbrugger, and Jean-Luc Lehners, have highlighted these difficulties. Attempts to fix them by modifying the proposal are ongoing, but the technical situation remains contested. The second problem is foundational. The no-boundary proposal assumes that the laws of quantum mechanics, the path integral, the Hilbert space, the quantum state, exist and are valid at the moment of the universe's origin. But those laws are themselves physical laws, presumably facts about our universe. If the universe didn't exist yet, in what sense did its laws exist? And if the laws pre-existed the universe, where did they live? Are mathematical truths independent of physical reality? This is not an idle question. It's the ancient debate between mathematical Platonism, the view that mathematical truths exist independently of minds or physical things, and alternative views still very much unresolved in philosophy. The third problem is physical. The no-boundary proposal is built on general relativity, modified by imaginary time. But virtually no physicist believes general relativity is the correct theory of gravity at the Planck scale. At those densities, quantum gravitational effects are so dominant that we need a theory of quantum gravity, which, as we've noted, we don't yet have. The no-boundary proposal might be the right answer in the framework of a future theory of quantum gravity, or it might be completely overturned by such a theory. We don't know, so the no-boundary proposal is a serious, historically important, philosophically profound idea that has shaped cosmological thinking for 4 decades. It might be right, but it might also be wrong. And if it's wrong, if time genuinely did exist before the Big Bang, or if the concept of before is meaningful in some deeper physical theory, then there really was a before, and the question of what it contained becomes not just legitimate but urgent. That is where the remaining theories come in. Before we get to the major pre-Big Bang cosmological theories, we need to spend time with a concept that underlies many of them, and that is extraordinary in its own right. The concept of the quantum vacuum, and why nothing in physics is not nothing at all. In classical physics, a vacuum is the absence of everything. No particles, no radiation, no fields, no energy. Total emptiness. The kind of nothing you might imagine if you tried to picture complete absence. Quantum mechanics destroys this concept completely. One of the foundational principles of quantum mechanics is the Heisenberg uncertainty principle. In its most famous form, it says that you cannot simultaneously know both the position and the momentum of a particle with arbitrary precision. The more precisely you know one, the more uncertain the other must be. But the uncertainty principle has another, equally important form. It applies to energy and time. The more precisely you know the energy of a system during a given time interval, the less precisely you can know the time. Or equivalently, during a sufficiently short time interval, the energy of a system can be uncertain by a large amount. The consequence of this is radical. Even in a perfect vacuum, even in a state with no particles, no radiation, the lowest possible energy, there must be quantum fluctuations. The energy of the vacuum cannot be precisely zero for a finite time interval, because if it were, we would know both its value, 0, and the time, with arbitrary precision, violating the uncertainty principle. Instead, the vacuum seethes with ephemeral fluctuations, virtual particles constantly appearing and annihilating, virtual photons winking in and out of existence, a restless microscopic churning that never stops. This is not metaphor. It is not a mathematical artifact. The quantum vacuum is physically real, and we can measure its effects. The most famous measurement is the Casimir effect, predicted by Dutch physicist Hendrik Casimir in 1948 and first measured in 1996. If you place 2 perfectly flat, perfectly conducting metal plates very close together in a vacuum, a tiny attractive force pulls them together. The reason is that the quantum vacuum fluctuations between the plates are constrained. Only certain wavelengths of virtual photons can fit in the gap, while fluctuations outside the plates are unconstrained. The difference in vacuum energy density creates a measurable force. This force has been measured to exquisite precision and matches theoretical predictions from quantum field theory extraordinarily well. The quantum vacuum also plays a role in the Lamb shift, a tiny displacement of certain energy levels in hydrogen atoms, in the anomalous magnetic moment of the electron, in the Unruh effect, in Hawking radiation from black holes, and in the dark energy that is currently accelerating the expansion of the universe. The vacuum is not nothing. It is a rich physical substrate governed by quantum laws, with energy, with fluctuations, with properties. It is the lowest energy state of quantum field theory, but it is very much a state of something. This realization opens up a remarkable possibility. In 1973, physicist Edward Tryon published a paper in the prestigious journal Nature with the provocative title, "Is the Universe a Vacuum Fluctuation?" The idea is audacious. Tryon proposed that the entire observable universe might have originated as an unusually large quantum fluctuation of the vacuum, a momentary excursion from the lowest energy state that, instead of collapsing back, somehow grew and stabilized into the universe we observe. Supporting this idea is a fascinating coincidence, or perhaps not a coincidence at all. If you carefully sum up all the positive energy in the universe, the kinetic energy of matter, the energy in electromagnetic radiation and so on, and all the negative energy, primarily the gravitational potential energy, which is negative because gravity is attractive and releasing gravitational energy requires pulling objects apart, the two might very nearly cancel. The total energy of the universe might be approximately zero. A universe with zero net energy can spontaneously arise from nothing without violating conservation of energy, because it has effectively borrowed nothing. It contains equal amounts of positive and negative energy, so the books balance. Lawrence Krauss popularized this idea in his 2012 book A Universe from Nothing, which generated both tremendous public interest and significant philosophical controversy. The philosophical controversy centered on what Krauss meant by nothing. He was using the term to refer to the quantum vacuum, a state with no particles, no structure, but governed by the laws of quantum field theory, containing virtual particle fluctuations, possessing quantum properties. Many philosophers, and some physicists, pointed out that this is emphatically not nothing in the metaphysically interesting sense. The quantum vacuum is something. It has properties. It obeys laws. It exists in some meaningful sense. Krauss's response was essentially pragmatic. We should let physics define what nothing means, rather than appealing to philosophical intuitions that may not map onto physical reality. And there's something to that argument. Physics has repeatedly forced us to revise our intuitive concepts when they don't match reality. Maybe nothing just is what quantum field theory says it is, the lowest energy quantum state, and demanding something more philosophically radical is a category error. But there's still a deep question lurking here. Even if the quantum vacuum can give birth to universes, the quantum vacuum itself operates according to the laws of quantum mechanics. Where do those laws come from? Why does the quantum vacuum exist rather than truly nothing? No laws, no vacuum, no mathematical structure, no anything. This is the question that philosopher of science David Albert raised in his influential review of Krauss's book, and it remains genuinely unanswered. Even if we can trace the universe's origin to a quantum fluctuation, we've only pushed the question back one step. Why was there a quantum vacuum to fluctuate in the first place? Physicist Alexander Vilenkin of Tufts University has proposed a way of taking this one step further. His tunneling from nothing proposal suggests that the universe could have originated by a quantum tunneling process from a state of literally no space, no time, no laws, genuine mathematical nothingness. The mathematics he uses to describe this is sophisticated, involving what are called instantons in quantum gravity, and the details are contentious. But the broad idea is that quantum mechanics might permit a transition from a state where no physical quantities exist, not even time, to a state where a small, smooth, inflating universe exists. The universe tunnels into existence from outside of existence. This is about as mind-bending as it gets, and it illustrates one of the recurring themes of this conversation. Every time physics tries to explain the beginning of the universe from something more fundamental, it inevitably relies on mathematical structures, laws, or quantum states that are themselves unexplained. The regress always continues. Whether that regress terminates in something self-explanatory, or in something external to physics, or whether it truly is infinite. That is the question that currently lies beyond the reach of physics to answer. Here is an idea that many physicists find genuinely compelling for a specific and important reason. It doesn't require the universe to have been born from nothing. Instead, it proposes that the universe has always existed in some form, cycling through a potentially infinite series of expansions and contractions, each one separated from the next by a dramatic but non-singular bounce at maximum density. This framework is called loop quantum cosmology, abbreviated LQC, and the central event it predicts is called the Big Bounce. Loop quantum cosmology is a branch of a larger theoretical project called loop quantum gravity, one of the two most serious and mathematically rigorous attempts currently underway to build a complete theory of quantum gravity. To understand what LQC proposes about the pre-Big Bang universe, you first need to understand the key physical insight at the heart of loop quantum gravity. In general relativity, space is a smooth, continuous mathematical manifold. You can zoom into arbitrarily small scales and space remains smooth. There is no minimum length, no granularity. This is a mathematical idealization that general relativity inherits from classical mechanics. But quantum mechanics teaches us that many apparently continuous quantities are actually discrete at the fundamental level. Light comes in discrete packets called photons. Energy levels in atoms are discrete. Electric charge comes in discrete multiples of the elementary charge. The quantum world is fundamentally granular. Loop quantum gravity proposes that space itself is granular at the deepest level. At the Planck scale, a length of about 10 to the negative 35 meters, space is not a continuous manifold, but a discrete network of interconnected quantum states called a spin network. Space, in this picture, is made of atoms. Not atoms in the chemical sense, but fundamental indivisible units of spatial geometry. The smallest possible volume of space is not zero, but a finite quantum of volume determined by the Planck scale. You cannot compress space to zero volume, any more than you can compress a gas to zero volume when you account for the fact that gas is made of atoms with finite size. This discreteness of space has a profound and specific consequence for cosmology. When you apply the mathematical framework of loop quantum gravity to a contracting universe, tracing backward in time from the present expanding universe, general relativity predicts that the universe collapses to a singularity, a point of infinite density and infinite curvature. But in loop quantum cosmology, the story is different. As the universe contracts and the density approaches the Planck density, roughly 10 to the power of 97 kilograms per cubic meter, which is almost incomprehensibly extreme, quantum geometric effects generate a repulsive pressure. This quantum gravitational repulsion is an automatic consequence of the discreteness of space. You cannot compress space to zero volume, so there is a minimum volume and a maximum density, and as the universe approaches these limits, the quantum pressure that resists further compression becomes enormous. This quantum pressure halts the contraction. Instead of collapsing to a singularity, the universe reaches a minimum volume at the Planck scale, and then bounces outward. The contraction becomes an expansion. The Big Bounce replaces the Big Bang singularity. What we observe as the Big Bang, the initial expansion of our universe from an extremely hot, dense state, is, in loop quantum cosmology, the outgoing phase of that bounce. This result has been worked out in impressive mathematical detail by physicists including Abhay Ashtekar at Penn State University, Martin Bojewald of Penn State, and Parampreet Singh, among others. The key technical result is that the LQC equations remain well-defined, deterministic and non-singular all the way through the bounce. The mathematical evolution of the universe can be traced continuously from the contracting pre-bounce phase, through the Planck scale bounce, and into the expanding post-bounce phase that we observe. There is no point where the equations break down. There is no singularity. The classical general relativistic singularity is resolved by quantum geometric effects. What was the universe like before the bounce? According to LQC, it was a contracting universe, a universe that, from the perspective of someone living in it, was evolving and possibly aging, contracting under the influence of gravity, its density increasing, heading toward the maximum density at which the bounce would occur. That universe might have had its own galaxies, its own stars, its own physics, or its matter might have been in a very different configuration. The details depend on which specific version of LQC you're working with and what initial conditions are assumed for the pre-bounce phase. One of the most important features of loop quantum cosmology is that it preserves information through the bounce, at least partially. In classical cosmology, the singularity is a one-way door. Nothing can pass through it and retain information about the universe before. But in LQC, the bounce is non-singular, and the quantum state of the universe on the contracting side determines, in a probabilistic quantum mechanical sense, the state on the expanding side. This means that, in principle, the present state of our universe, the specific fluctuations in the CMB, the particular distribution of matter on large scales, contains imprints of the pre-bounce universe. The universe remembers its past, at least partially, even across the bounce. This has a crucial implication. LQC makes observational predictions, not predictions about direct observation of the pre-bounce universe, that's impossible in any framework, but predictions about the statistical properties of the CMB and the primordial power spectrum of density fluctuations that we can and do measure. Different versions of LQC predict slightly different spectra of primordial fluctuations compared to the standard inflationary model. Future CMB experiments, with their ever-increasing sensitivity, might be able to distinguish between these predictions, and thereby provide evidence for or against the big bounce. This distinguishability is what separates a scientific theory from mere speculation. A theory that makes no testable predictions, however mathematically sophisticated, is not science. It's mathematics with physical ambitions. LQC, whatever its remaining uncertainties, makes real predictions that real experiments might be able to test. There is also a beautiful cyclical possibility within LQC. If the universe bounces from a contracting phase into an expanding phase, what caused the previous universe to contract in the first place? Perhaps the universe before the bounce was also the result of a previous bounce, an expanding universe that slowed, turned around, and contracted. And before that, another bounce, and before that, another. Under some versions of loop quantum cosmology, this chain of bounces could extend back infinitely into the past, giving us a universe that has no first moment, no beginning, no before the beginning at all. Just an infinite sequence of cycles, each one an era of expansion followed by contraction, followed by bounce, stretching back forever. This is a philosophically satisfying picture in some ways. It avoids the discomfort of both something from nothing and it just started. But it raises its own deep questions. If the chain of bounces extends back infinitely, does the universe's entropy, a measure of its disorder, increase monotonically through each cycle? If so, what does the universe look like after an infinite number of cycles toward higher entropy? These questions are actively being researched. The answers depend on details of LQC that remain to be worked out, but the framework is rich enough that these questions have precise formulations and could, in principle, have answers. String theory is the other great candidate for quantum gravity, and it offers a completely different and stranger picture of what might have preceded the Big Bang, one that involves objects you can barely conceptualize, operating in dimensions of space you cannot directly observe. String theory's central proposal is that the fundamental constituents of reality are not point particles, not tiny zero-dimensional dots, but incredibly small, one-dimensional vibrating strings of energy. These strings are extraordinarily tiny, thought to be about the Planck length in extent, roughly 10 to the negative 35 meters, which is about 20 orders of magnitude smaller than a proton. From any larger scale, a string looks like a point, which is why we've always thought of fundamental particles as point-like. But at the Planck scale, these strings vibrate in different modes, and each mode corresponds to a different type of particle. An electron, a quark, a photon, a graviton. All of these are, in string theory, the same fundamental object, a string, vibrating in different ways. The mathematically beautiful and physically important thing about string theory is that one of its vibrational modes, a massless spin-2 mode, has exactly the properties of the graviton, the hypothetical quantum carrier of the gravitational force. This means gravity emerges naturally from string theory, which is why it's considered such a promising candidate for quantum gravity. Previous attempts to quantize gravity as a field theory in 4 dimensions failed. because they produced infinitely large answers for all physical quantities, as thus they were non-renormalizable. String theory avoids these infinities because strings have a finite size. The stringy nature of particles acts as a natural ultraviolet regulator. But string theory requires more dimensions than we observe. The mathematics works, is self-consistent, only if space-time has 10 dimensions, 9 of space and 1 of time, for string theory, or 11 dimensions for M-theory, the broader framework that includes and unifies the 5 different versions of string theory. The 6 or 7 extra spatial dimensions beyond the 3 we observe are thought to be compactified, curled up into incredibly small geometric shapes at the Planck scale, far too small to detect directly with any existing technology. M-theory introduces objects beyond strings, multi-dimensional membranes called branes, short for membranes. A 1 brane is a string, a 2 brane is a membrane, a surface, a 3 brane is a 3-dimensional volume, and so on up to 9 branes. In M-theory, our observable universe is thought to live on a 3 brane, a 3-dimensional membrane embedded in a higher dimensional bulk space. We are in this picture like bugs living on the surface of a soap bubble, unable to perceive the space around the bubble but definitively embedded in it. Other branes might exist in the bulk, parallel to ours, invisible to us because ordinary matter and light, which is electromagnetic radiation governed by Maxwell's equations, is confined to our brain and cannot propagate through the bulk. The one thing that can propagate through the bulk is gravity, because gravity is a property of the geometry of all dimensions of space-time, not confined to any particular brane. This means that the other brane, if it exists, exerts a gravitational influence on our brain, even though we cannot see it or detect it electromagnetically. Now we can arrive at the ekpyrotic model, proposed in 2001 by physicists Justin Curie of Princeton, Bert Overath of the University of Pennsylvania, Paul Steinhardt of Princeton, and Neil Turok of Cambridge. The name comes from the ancient Greek word ekpyrosis, meaning a great conflagration, a reference to the Stoic philosophical idea of the universe being periodically consumed by fire and reborn. The ekpyrotic model proposes that our Big Bang was the result of a collision between 2 branes. Picture 2 enormous, nearly parallel 3 branes, floating in a 5-dimensional bulk space, our brain and another brane, sometimes called the hidden brane, hovering some distance away. Both branes are essentially flat, empty and cold. They are not expanding dramatically. Time passes slowly and uneventfully on both branes. But they are attracted to each other by gravity propagating through the bulk. Over an enormously long period of time, potentially many trillions of years, they drift slowly toward each other. Eventually they collide. The kinetic energy of the collision, the energy of 2 vast membranes crashing together, is deposited on our brain as heat and radiation. In an instant, our brain goes from cold and empty to fiercely hot and dense. The collision triggers a rapid expansion of our brain, and that, the moment of collision, is what we call the Big Bang. This picture has several immediately striking features. First, there was a before the Big Bang in a completely ordinary temporal sense. Time existed, physics existed, events happened, our brain existed, the other brain existed. They were drifting toward each other over vast stretches of time that preceded the collision. Second, there was no singularity. The collision of 2 branes in a higher dimensional bulk does not require a point of infinite density. It's a finite energy event in a higher dimensional space. Third, the flatness and smoothness of the universe, features that inflation was invented to explain, arise naturally in the ekpyrotic model because the branes themselves are flat and smooth before the collision, and that flatness is imprinted on our post-collision universe. Paul Steinhardt and Neil Turok extended this into a fully cyclic framework. In their cyclic model, the Big Bang is just one of an infinite series of collisions. After our collision, our universe expands, cools, galaxies form, stars live and die, and eventually, after many trillions of years, some physical mechanism causes the branes to attract each other again. They drift together, collide, produce another Big Bang, and the cycle repeats, infinitely into the past and infinitely into the future. No first collision, no last one. The string theory landscape adds another layer to this cosmic picture. String theory admits an enormous number of different stable compactifications of the extra dimensions. different ways of curling the extra dimensions into their tiny shapes, each corresponding to different values of fundamental constants, different particle masses, different physical laws. Current estimates put the number of such solutions at something like 10 to the power of 500. This vast collection of possible physical laws is called the string landscape. The cyclic model, in its most expansive form, imagines that each collision can produce a universe with different properties depending on how the extra dimensions are configured after the collision. Over the infinite series of cosmic cycles, every possible set of physical laws might eventually be realized. We find ourselves in the particular universe we inhabit because it's one of the configurations that permit stars, planets, and observers. One of the most successful and consequential ideas in all of modern cosmology is cosmic inflation. In 1979 and 1980, Alan Guth at MIT developed the inflationary model of the universe, building on earlier work by Alexei Starobinsky in Moscow, and it transformed the field. Before inflation, the Big Bang model had several embarrassing gaps, things it could not explain. Inflation filled those gaps. But inflation also opened a door to something much larger and stranger, the possibility that our universe is just one bubble in an infinite, eternally expanding cosmic sea. Let's start with what inflation is and why it was needed. The standard Big Bang model without inflation faces three major problems. The first is the flatness problem. General relativity tells us that the geometry of the universe depends on its energy density. If the density is above a critical value, the universe is positively curved, like a sphere. If it's below, it's negatively curved, like a saddle. If it's exactly equal, it's flat. Observations tell us our universe is very close to flat. But here's the problem. In the standard Big Bang model without inflation, flatness is an unstable condition. If you start with a universe that's even slightly different from perfectly flat, those deviations grow over time. For the universe to be as flat as we observe it today, nearly 13.8 billion years into its history, it would have needed to be extraordinarily, precisely, almost impossibly flat at the Planck epoch. The required precision is something like 1 part in 10 to the 60. That seems to demand a cosmic fine-tuner. The second is the horizon problem. The CMB is uniform in temperature to 1 part in 100,000 across the entire sky. But if you look at two opposite parts of the sky, directions 180 degrees apart, the radiation from those directions was emitted at regions of the universe that, in the standard Big Bang, were too far apart to have ever been in causal contact. Light from one region could not have reached the other by the time the CMB was emitted. So how did they come to be at exactly the same temperature? They couldn't have communicated to agree on a temperature. This is the horizon problem. The third is the magnetic monopole problem. Many grand unified theories of particle physics predict that exotic particles called magnetic monopoles, particles with a net magnetic charge, unlike the dipole magnets we observe, should have been produced in abundance in the hot, dense early universe. Yet no magnetic monopole has ever been detected. Inflation solves all three problems elegantly. The idea is that the universe underwent a period of incredibly rapid, exponential expansion in the first fractions of a second after the Big Bang. Expansion so fast that the universe doubled in size at least 80 times, and possibly far more, in an interval shorter than 10 to the negative 32 seconds. This expansion was driven by the energy of a quantum field called the inflaton, in what physicists call a false vacuum state, a high-energy quantum state that is temporarily stable, but will eventually decay to a lower-energy true vacuum state. During inflation, the universe expanded so rapidly that any curvature was stretched to enormous scales, making the observable universe look flat locally. The flatness problem is solved. Any initial region of the universe small enough to be in thermal equilibrium was stretched to sizes far larger than the observable universe. The horizon problem is solved, because what we observe as the entire visible sky was once a tiny, thermally uniform patch. And any magnetic monopoles produced before inflation began were diluted to densities so low that we'd expect fewer than one in the observable universe. The monopole problem is solved. Furthermore, inflation provides a mechanism for generating the small density fluctuations that became the seeds of galaxies. Quantum fluctuations in the inflaton field, stretched by inflation to cosmic scales, became the density variations we observe in the CMB. The predicted spectrum of these fluctuations, called the Harrison-Zeldovich-Peebles spectrum, has been confirmed by CMB observations to extraordinary precision. This is one of the great predictive successes of modern cosmology. Now, here's where the picture explodes in scale. Guth, Lind, and others realized almost immediately that inflation, once started, has a remarkable property. It is almost impossible to stop everywhere simultaneously. The inflaton field doesn't evolve uniformly, it's a quantum field subject to quantum fluctuations. In any given region of space, the inflaton field is rolling toward its lower energy true vacuum state, but quantum fluctuations kick it around, sometimes rolling it a little higher instead of lower. In regions where the quantum kick pushes the field higher, inflation continues. In regions where the field rolls low enough to decay to the true vacuum, inflation ends and a hot Big Bang occurs locally. But the regions where inflation continues are expanding exponentially, so they are always vastly larger than the regions where it has ended. The net result is that while inflation ends locally in some regions, producing hot Big Bangs, producing universes like ours, it continues globally, forever. This is eternal inflation. It is self-perpetuating, self-replicating, unending. As Guth famously said, it's hard to build models of inflation that don't lead to a multiverse. The inflationary background, the vast exponentially expanding sea of false vacuum energy, never terminates. It exists forever, perpetually spawning new bubble universes as local regions decay from false vacuum to true vacuum. Each bubble is a universe in its own right. It has its own hot Big Bang, its own expansion history, its own long-term evolution. In the context of the string landscape, with its 10 to the 500 possible vacuum states, each bubble universe might settle into a different vacuum state, giving it different fundamental constants, different particle masses, different laws of physics. The inflationary multiverse would then be an infinite collection of bubble universes, each with its own physics, most of them wildly different from ours, with only the small fraction that happen to have life-permitting physical laws hosting observers to notice. From the perspective of someone in our bubble universe, what happened before our Big Bang? The answer in eternal inflation is more inflation. Before our bubble nucleated, the inflationary background existed. It had been running, how long? Possibly forever, although theorems by Borde, Guth and Vilenkin suggest that the inflationary background, even if eternal into the future, was probably not eternal into the past. It had to have started at some finite time in the past. What started it is one of the remaining great open questions. Eternal inflation is perhaps the most widely accepted framework among working cosmologists for describing the broader context in which our universe exists. Not because all its features are proven, they're not, but because once you accept inflation, which the CMB data strongly support, eternal inflation follows almost automatically from the mathematics. The multiverse is not an add-on to inflation, it's a consequence of it. Roger Penrose is one of the most creative and rigorous mathematical physicists of the 20th and 21st centuries. His work with Hawking on singularity theorems in the 1960s and 1970s established fundamental results about the structure of general relativistic spacetimes. His work on twistor theory opened a new approach to unifying quantum mechanics and gravity. His contributions to the mathematics of spacetime structure are foundational. In 2020, at the age of 89, he received the Nobel Prize in Physics for his singularity theorem work. He is also the author of one of the most ambitious and original pre-Big Bang theories currently under active discussion, conformal cyclic cosmology, or CCC. CCC is built on a chain of ideas that starts with something most people have never thought carefully about. What happens to the universe in the very far future? Under our current understanding, the universe is expanding and the expansion is accelerating. Driven by dark energy, a form of energy inherent to empty space, the universe will continue to expand faster and faster. Galaxies that are currently visible will recede beyond our cosmological horizon and become forever unobservable. The Milky Way will eventually merge with the Andromeda Galaxy, as the two are gravitationally bound, and will collide in about 4 billion years. But beyond our local group of galaxies, all other galaxies will eventually recede beyond detection. Stars will burn out. The last red dwarf will flicker and die perhaps 100 trillion years from now. The universe will grow dark. Then, over even longer timescales, vastly longer, measured in numbers with googolplex digits, black holes will dominate. Stellar remnants, planets, any remaining structures will be gradually devoured by black holes. These supermassive black holes at the centres of dead galaxies will consume everything in their gravitational reach, and then even the black holes will die. Stephen Hawking discovered in 1974 that black holes are not perfectly black. They emit faint thermal radiation, now called Hawking radiation, as a consequence of quantum mechanics near their event horizons. Over the course of their lifetimes, black holes radiate away all their mass and evaporate completely. For supermassive black holes, this takes an almost incomprehensibly long time, something like 10 to the power of 100 years, but it happens eventually. At the end of all this, after the stars and the black holes are gone, what remains? The universe is filled with photons, neutrinos, gravitons, and other massless particles flying through an enormous, expanding, cooling, utterly dark cosmos. This is the heat death of the universe, the maximum entropy state, in thermal equilibrium, with nothing left to do. Now, Penrose noticed something specific and important about this final state. It contains only massless particles, and massless particles, photons, gravitons, have a profoundly special property. They experience no proper time. From the perspective of a photon, the moment it is emitted and the moment it is absorbed are the same moment. There is no duration. There is no clock. If you tried to synchronize clocks using massless particles in this final state of the universe, you could not, because the clocks would require some material medium to function, and all material has decayed. This means that in the far future, when the universe contains only massless radiation, time, in a precise physical sense, has lost its operational meaning. There are no clocks. There are no massive objects to define a time standard. The concept of how long becomes undefined. Penrose then makes a deep mathematical observation. The geometry of a spacetime containing only massless particles has a special symmetry called conformal invariance. Conformal geometry is a branch of geometry that preserves angles and local shapes but not distances or scales. You can stretch or shrink a conformally invariant geometry by any smooth function, and it remains physically equivalent because everything in it, massless particles in this case, is scale invariant. Here is the key. A universe filled only with massless radiation, at the end point of its expansion, has no preferred scale. It looks the same regardless of whether you define lengths in meters or in light years. Infinite size is conformally equivalent to any finite size. And Penrose proposes something extraordinary. The conformal geometry of this infinitely expanded, massless-dominated future universe is identical, mathematically indistinguishable, to the conformal geometry of the Big Bang singularity of the next universe. This is conformal cyclic cosmology. The infinitely expanded future of one cosmic aeon becomes the Big Bang of the next aeon, through a conformal rescaling. There is no contraction. There is no bounce in the usual sense. Instead, the universe reaches such a state of extreme dilution and masslessness that its geometry is conformally equivalent to the beginning of a new universe, and a new cosmic cycle begins. The two eons are joined across what Penrose calls a crossover surface. The previous aeon, the universe before our Big Bang, was itself a complete cosmos, lasting from its own Big Bang through its own billions of years of stellar evolution, black hole formation, and ultimate evaporation, until its own heat death, at which point the conformal identification brought it into our Big Bang. And before that previous aeon there was another, and before that another, an infinite regress of aeons, each one a complete universe, each one giving birth to the next through this conformal mechanism. What makes this scientifically exciting rather than merely philosophically speculative is that CCC makes a specific prediction. The gravitational waves produced by the final collisions and evaporation of supermassive black holes in the previous aeon, specifically the burst of gravitational radiation released when a large black hole finally evaporates, would propagate through the conformal crossover into our aeon and leave an imprint in the cosmic microwave background. These imprints, which Penrose calls Hawking points, should appear as circular patterns of slightly elevated temperature in the CMB, centered on the locations where those final black holes from the previous aeon evaporated. Penrose and collaborators, including Vahe Gurzardian, have claimed to detect these Hawking points in CMB data. The claim is controversial. Multiple independent groups, using different statistical methods and different analyses of the same Planck satellite data, have looked at the results and concluded that the claimed signals are consistent with what you'd expect from purely random fluctuations in the CMB without any pre-Big Bang signal. The debate is ongoing and unresolved. It is a live scientific controversy of exactly the kind that science is supposed to have: competing analyses, transparent methods, data open to scrutiny, and results that are not yet settled. The biggest theoretical challenge for CCC is the question of what happens to massive particles in the far future. The standard model of particle physics predicts that the electron is absolutely stable. It cannot decay into anything lighter, because there is nothing lighter with the same charge. For CCC to work, all massive particles, including the electron, must eventually decay into massless ones. This would require new physics beyond the standard model. Penrose acknowledges this and considers it a potentially real prediction of his framework. A prediction that could, in principle, be tested if proton decay, a similar prediction of grand unified theories, is eventually observed, or if new physics beyond the standard model is discovered. CCC is a minority view in the cosmology community, but it comes from one of the greatest minds in the history of theoretical physics. It is mathematically rigorous. It makes specific predictions, and it cannot be dismissed as crank science. It is exactly the kind of bold, original theoretical proposal that science needs to have on the table. We have now toured the major theoretical landscape of pre-Big Bang cosmology. We've met the Big Bounce, the brane collision, the eternal inflationary sea, the conformal cyclic aeons, and the quantum tunneling from nothing. Each is a genuine, mathematically serious proposal. And here we must be honest about something that is deeply important and often glossed over in science communication. We cannot currently tell which of these frameworks, if any, is correct. And there are fundamental reasons why establishing that may be extremely difficult, or in some cases, permanently impossible. Let's think carefully about why. The first barrier is the surface of last scattering. The cosmic microwave background, as we discussed, represents the oldest light in the observable universe, light emitted 380,000 years after the Big Bang, when the universe first became transparent. Before that moment, the universe was opaque to electromagnetic radiation. We cannot use light to observe the universe before 380,000 years of age, no matter how powerful our telescopes become. The CMB is our electromagnetic wall, the maximum depth we can peer back in time using photons. This is not a limit that will be overcome by building bigger telescopes. It is a fundamental limit set by the physics of the early universe. Any observations of conditions before the CMB epoch must use something other than light. Gravitational waves are the primary candidate. Because gravitational waves interact so weakly with matter, they can penetrate the hot, dense plasma of the early universe that photons could not escape. If the early universe produced gravitational waves, as it would during inflation, during a bounce, or during a brane collision, those waves propagate freely through the plasma and are present today as a gravitational wave background. Different theoretical scenarios predict different characteristics of this primordial gravitational wave background, and detecting it would provide invaluable information about the early universe. The Laser Interferometer Space Antenna, or LISA, is a space-based gravitational wave observatory being developed by the European Space Agency for launch in the early 2030s. LISA would be sensitive to gravitational waves at much lower frequencies than LIGO, which makes it more sensitive to the primordial gravitational wave background from inflation and other early universe processes. Third-generation ground-based detectors, the Einstein Telescope in Europe and Cosmic Explorer in the United States, are also planned and would have far greater sensitivity than current LIGO/Virgo detectors. There is also the CMB itself. Future CMB experiments, particularly CMB-S4, a next-generation CMB observatory to be built at the South Pole, will map the polarization of the CMB with sensitivity 50 times greater than current instruments. One of CMB-S4's primary scientific goals is to detect the B-mode polarization pattern that primordial gravitational waves from inflation would imprint on the CMB. Detecting this signal, or tightly constraining it to be below detection, would powerfully constrain inflationary models and alternatives. But here is the second and deeper barrier. Even if we detect the gravitational wave background from the inflationary epoch, or extract every bit of information encoded in the CMB we're still observing the universe long after the Planck epoch. The Planck epoch, the first 10 to the negative 43 seconds, is the regime where quantum gravity effects dominate and our current physics breaks down. Any signal from before the Planck epoch has been processed and transformed by the chaotic dynamics of the Planck epoch itself, the violent physics of the hot Big Bang, the processes of nucleosynthesis, recombination, and 13.8 billion years of cosmic evolution. Extracting information about the pre-Planck epoch from such a signal is like trying to reconstruct the original sound in a room from the echoes that have bounced around for billions of years. The original signal is encoded in those echoes, but reading it requires knowing everything about how the room behaves, which, for the early universe, requires a complete theory of quantum gravity. The third barrier is the question of testability for the multiverse scenarios. In eternal inflation, the other bubble universes are, by definition, causally disconnected from ours. They are separated by inflationary regions expanding faster than light. No signal from them can ever reach us. We will never observe another bubble universe directly. The predictions of eternal inflation that we could in principle test are predictions about the statistics of the properties of universes, predictions that require an account of the probability measure across the inflationary landscape, which is itself deeply contested. The measure problem in eternal inflation, the question of how to compute probabilities in an infinitely large multiverse, is one of the most difficult open problems in theoretical cosmology. This raises the fundamental question of whether eternal inflation, in some of its formulations, is really a scientific theory at all. A scientific theory must make predictions that could in principle be wrong. It must be falsifiable, in Karl Popper's terminology. If a theory predicts an infinite multiverse where every possible set of physical laws is realized somewhere, it can accommodate any possible observational result, and a theory that can accommodate anything predicts nothing. Some physicists, including Lee Smolin and Paul Steinhardt, have made exactly this criticism of the inflationary multiverse. The defenders of eternal inflation and the multiverse respond in several ways. Some argue that falsifiability is too narrow a criterion for scientific acceptability, that mathematical consistency, explanatory power, and theoretical elegance are also legitimate scientific virtues. Others argue that the multiverse makes genuine predictions, for example, anthropic predictions about the values of fundamental constants that permit observers to exist, that are in principle testable. Still others argue that the measure problem will eventually be solved in a way that makes specific, testable predictions. This debate is not resolved. It is one of the most active discussions in the philosophy of physics, and it's a genuine and important discussion to have. This question, what was here before the Big Bang, does not exist only in the domain of physics. It sits at the crossroads of science, philosophy, and theology in ways that cannot be ignored without intellectual dishonesty, and it demands engagement across all three. The question of whether the universe requires an explanation external to itself is perhaps the oldest question in human philosophical and religious thought, and it has not gone away. If anything, modern cosmology has sharpened it. Let's start with the theology. Every major religious tradition has a creation narrative. In the Abrahamic traditions, Judaism, Christianity, and Islam, the universe was created by God, who existed before the universe and who brought it into being. The opening of Genesis, "In the beginning God created the heavens and the earth," is straightforwardly a claim that God pre-existed the universe and was its creator. Classical Islamic theology holds that God is uncreated, eternal, and the first cause of all things. Thomas Aquinas, the great medieval Christian philosopher, argued that everything that moves is moved by something else, and this chain cannot regress infinitely, so there must be an unmoved mover, what we call God. Many religious thinkers, and many religious scientists, saw the Big Bang as a confirmation of the theological position. If the universe had a beginning, it had a cause, and what could that cause be but God? Pope Pius XII famously declared in 1951 that the Big Bang theory confirmed the truth of Genesis, but this reaction actually caused some discomfort in the scientific community, because it seemed to suggest that theology was looking to physics to validate its claims, which would make theology empirically vulnerable. If the Big Bang were later found to be preceded by a prior state, what would happen to the theology? Georges Lemaitre himself, the Catholic priest and physicist who first proposed the Big Bang model, was uncomfortable with the Pope's declaration. He insisted that his hypothesis was a scientific one, to be judged on scientific grounds, and that science and theology should operate independently. When Lemaitre learned of Pius XII's 1951 speech, he reportedly sought out and persuaded the Pope not to make such pronouncements in future. The modern philosophical version of the theological argument is the Callum cosmological argument, championed by philosopher William Lane Craig. Simplified: 1. Everything that begins to exist has a cause. 2. The universe began to exist. 3. Therefore the universe has a cause. The cause of the universe, Craig argues, must be something that is itself uncaused, timeless, spaceless, immensely powerful, which is what religious traditions mean by God. Modern physics complicates this argument in interesting ways. If loop quantum cosmology is correct, the universe didn't begin to exist. It has been cycling through bounces eternally, with no first moment. Premise 2 of the Callum argument is then false. If eternal inflation is correct, the universe, or at least the inflationary background, might be eternal, again falsifying premise 2. If the Hartley-Hawking no-boundary proposal is correct, time itself began with the universe, which makes the concept of cause, which involves temporal priority, inapplicable, and the argument breaks down in a different way. Craig responds that even an eternal cycling universe would require an explanation of why it has the properties it does, and why it exists rather than not existing. This leads to the deeper philosophical question raised by Leibniz: why is there something rather than nothing? Leibniz's principle of sufficient reason holds that everything must have an explanation for its existence and properties. Even if the universe is eternal, even if it has always existed, its existence is contingent, not necessary. It could have been otherwise. There could have been nothing at all. And this contingency seems to demand an explanation. The theist says the explanation is a necessarily existing God. The naturalist says either that the universe explains itself through its own mathematical structure and the laws of quantum mechanics, or that the question has no answer. The universe's existence is a brute fact, and demanding further explanation is a mistake. Sean Carroll, physicist at Johns Hopkins, argues forcefully for the brute fact position. He suggests that the laws of nature might be self-explanatory, that a universe governed by the laws of quantum mechanics simply is what it is, and asking why those laws exist rather than some others, or why anything exists rather than nothing, might be category errors, questions that sound meaningful but don't actually demand coherent answers. The universe, in Carroll's view, has no explanation outside itself, not because the question has been answered, but because the concept of explanation runs out when applied to the universe as a whole. Philosopher of physics Tim Maudlin takes a different view. He argues that the mere existence of physical reality genuinely cries out for explanation, and that dismissing this as a category error is too quick. The existence of something rather than nothing is not obviously a malformed question. It seems perfectly meaningful to imagine there being nothing, and the fact that there is something instead seems to demand an account. What is striking is that this debate, among some of the best trained and most thoughtful people working on the hardest questions in physics and philosophy, has not been resolved. We are genuinely, authentically uncertain about whether the universe requires an explanation that transcends it, whether such an explanation is even coherent, and whether physics can or cannot say anything useful about it. And this uncertainty is intellectually honest. It would be dishonest to pretend in either direction that the question is settled. What we can say with confidence is that modern cosmology has not resolved the question of ultimate origins. It has pushed it back, reframed it, made it more precise, and revealed its extraordinary difficulty. Whether the answer is a pre-existing God, an eternal quantum vacuum, an infinite chain of bouncing universes, or simply the universe's own self-contained mathematical structure that remains genuinely open. The field of pre-Big Bang cosmology is not static. It is among the most active and rapidly evolving areas of theoretical physics, and new observational capabilities will test its ideas in the coming years and decades in ways that were impossible even recently. The next generation of CMB experiments is perhaps the most important near-term development. CMB-S4, the fourth generation CMB Stage 4 experiment being planned by a collaboration of US institutions, will deploy tens of thousands of detectors at observatories at the South Pole and in the Atacama Desert of Chile. Its primary scientific goal is to detect the B-mode polarization of the CMB at the level expected from inflationary models, or to push constraints low enough to rule out the simplest inflationary models and favour alternatives. The gravitational wave backgrounds predicted by the Big Bounce of loop quantum cosmology, by the ekpyrotic scenario, and by various versions of inflation are all different, and CMBS4 has the potential to begin distinguishing between them. Gravitational wave astronomy is in an explosive growth phase. LIGO, Virgo, and Kagra have transformed our ability to observe the universe through gravitational waves rather than light. Future observatories will push this much further. LISA, the Laser Interferometer Space Antenna, will consist of 3 spacecraft in a triangular formation millions of kilometers apart, forming a gravitational wave detector of unprecedented sensitivity at low frequencies. LISA is expected to be sensitive to the stochastic gravitational wave background produced by processes in the very early universe, including inflation, phase transitions, and other exotic phenomena. The Einstein telescope, a proposed underground European detector with arms 10 kilometers long, compared to LIGO's 4 kilometers, would be sensitive to even fainter signals from even further in the past. If we detect the primordial gravitational wave background, and if the signal is strong enough to characterize its spectral properties, we will gain an unprecedented window into the first fractions of a second of cosmic history, and potentially, through the quantum gravity fingerprint in that signal, into whatever preceded that epoch. Numerical relativity, the computational solution of Einstein's equations on supercomputers, is also emerging as a powerful probe of early universe physics, as described in a 2025 paper by Eugene Lim of King's College London and colleagues published in Living Reviews in Relativity. Numerical relativity can be used to model scenarios that have no analytical solution, including inhomogeneous pre-Big Bang scenarios, multiverse bubble collisions, and the details of the quantum bounce in loop quantum cosmology. These computational approaches allow theorists to make more realistic and detailed predictions than analytical methods alone. The James Webb Space Telescope is providing astonishing views of the earliest galaxies, some seen as they were when the universe was only a few 100 million years old. Some early JWST results have surprised cosmologists by revealing galaxies that appear more massive and structurally mature than the standard model's predictions for that epoch. Whether this represents new, early universe physics, perhaps connected to a pre-Big Bang era, or whether it reflects gaps in our understanding of galaxy formation within the standard model, is being actively investigated. If the discrepancy is real and grows with more data, it could point to modifications of the standard cosmological model with implications for the very early universe. Quantum information theory is increasingly intersecting with cosmology in productive ways. The black hole information paradox, whether information is preserved when matter falls into a black hole and the black hole subsequently evaporates, has driven enormous theoretical progress in understanding the relationship between quantum mechanics, gravity, and information. Ideas like holography, the suggestion that the information in a three-dimensional spacetime can be encoded on a two-dimensional surface, and the ADS/CFT correspondence are reshaping how physicists think about quantum gravity. These ideas are increasingly being applied to cosmological questions, including the question of what happened at and before the Big Bang. Some researchers believe that the key to understanding pre-Big Bang physics lies precisely in understanding how quantum information is processed in cosmological settings. There is also the ongoing uncertain search for dark matter. Dark matter makes up 27% of the total energy content of the universe and plays a central role in structure formation. Without it, galaxies as we know them would not have formed. We know dark matter exists from its gravitational effects, but we have not detected a dark matter particle. If we do detect dark matter, and if its properties reveal something about the physics of the very early universe, as some models of dark matter connect it to physics at extremely high energy scales, that could provide new insights into early universe conditions and their possible pre-Big Bang origins. And always, lurking in the background, is the possibility that an unexpected discovery changes everything. The history of physics is littered with transformative surprises. The discovery that the expansion of the universe is accelerating, announced in 1998, winning the Nobel Prize in 2011, was completely unexpected and forced a wholesale revision of cosmological models. The first detection of gravitational waves in 2015 opened an entirely new observational window. The James Webb Space Telescope images of early galaxies are already challenging expectations. The next transformative discovery might be just around the corner, or it might be decades away, but its probability of occurring within the lifetimes of people reading this is not small. This might seem like an odd section for a cosmology video, but it's one I think is worth including, because these questions, the ones we've been exploring tonight, are not only about the universe, they're about us. Think about what it means that we're asking this question at all. The matter that forms your brain, every carbon atom, every hydrogen atom, every atom of every element in your body, was forged in the nuclear furnaces of stars that lived and died before our solar system existed. The iron in your blood was synthesized in a supernova explosion. The oxygen you breathe was produced in the thermonuclear reactions of a long-dead star. You are, in the most literal sense, made of stardust. And you are the part of the universe that is able to look back at 13.8 billion years of cosmic history and ask, how did all of this come to be? What came before? That question, asked with full sincerity and pursued with the tools of mathematics and observation, represents something genuinely extraordinary in the history of the cosmos. For most of the universe's history, the universe just was. Matter, following the laws of gravity, stars burning and dying, galaxies forming and evolving, but no awareness of any of it. Then, about 4.5 billion years ago, a rocky planet formed around an ordinary star in an ordinary galaxy. Eventually on that planet, through processes we are still working to understand, matter organized itself into living things. Those living things evolved, and eventually, in what is the tiniest sliver of cosmic time, conscious, curious minds appeared. Those minds built instruments that can detect gravitational waves from black holes a billion light-years away. They derived mathematical equations that describe the behavior of space-time at energies trillions of times higher than any particle accelerator can reach. They mapped the oldest light in the universe to better than 1 part in 100,000. And they are now genuinely grappling with the question of what came before the universe's birth. There's a specific quality of mind required for this endeavor that I want to name explicitly. It requires the willingness to be wrong. It requires intellectual humility of a kind that is genuinely difficult. Every one of the theories we've discussed tonight might be completely incorrect. Loop quantum cosmology might be wrong about the discrete structure of space. Eternal inflation might be right about inflation, but wrong about eternal self-replication. The ekpyrotic model might be an interesting mathematics problem without physical relevance. Even the Hawking-Hartle no-boundary proposal might be abandoned when we finally have a working theory of quantum gravity. Science advances by being wrong, noticing it's wrong, and correcting itself. The physicists working on these theories know this. They know that most of the hypotheses proposed in any generation of science turn out to be wrong. They propose them anyway, because proposing a specific testable hypothesis and being wrong is far more useful than proposing nothing. Each wrong answer narrows the space of possibilities. Each failed prediction teaches us something about the constraints the correct theory must satisfy. The willingness to be wrong in public, to publish a theory that might be refuted, and to carry on anyway, to update your views when the evidence demands it, is what separates the scientific approach from dogmatism in any form. And it's what gives science its extraordinary track record of progress, even in the face of problems that seemed, at first glance, completely intractable. The pre-Big Bang universe is one of those problems. It's intractable right now. But intractable right now has a remarkable historical track record of becoming understood later. There is a specific kind of vertigo that comes from standing at the genuine edge of human knowledge and looking outward. Not the comfortable vertigo of a popular science book that assures you the answer is almost within reach. The real thing, the recognition that we are genuinely, profoundly uncertain about something fundamental, and that this uncertainty might not be resolved in our lifetimes. The question of what came before the Big Bang induces exactly that vertigo, and I want to sit with it for a moment before we close. We know that approximately 13.8 billion years ago, the universe was in an extremely hot, dense state, and began expanding. We know this with high confidence. We can measure the afterglow of that expansion in every direction, to exquisite precision. We can trace the history of the universe from that initial hot, dense state forward to today, accounting for the formation of hydrogen and helium in the first minutes, the slow assembly of galaxies over billions of years, the birth and death of stars, the emergence of planets, and eventually the emergence of life. but we do not know what that initial hot, dense state emerged from. We do not know if there was a from, if the question even makes sense. We have serious, carefully developed theories: the quantum bounce, the brane collision, the eternal inflationary background, the conformal cyclic aeon, the quantum tunneling from nothing. Each of these theories has mathematical substance. Each is the product of brilliant minds working with sophisticated tools. Each captures something potentially real about the structure of the cosmos at its most fundamental level, and we cannot currently tell which is right. We might not be able to tell for decades. Some aspects of the question might be permanently beyond our observational reach. This is not a failure of science. It is science being honest about where its current reach ends. It is science at the frontier, not at the comfortable interior of well-established territory, but at the ragged, uncertain edge where the maps run out and the real exploration begins. The people working on these questions know they might be wrong. They know that the theory they've spent their careers developing might be overturned by the next generation, and they work on anyway, because the alternative, not trying, not pushing, accepting permanent ignorance about the most fundamental question possible, is unacceptable to a certain kind of mind. The kind of mind that can't help but look at the edge of the known and feel the pull of what's beyond. The question of what came before the Big Bang is the deepest question physics has ever confronted. It may be deeper than physics can answer alone. It may require the development of entirely new conceptual frameworks that don't yet exist. It may require experiments not yet designed, detecting signals not yet predicted, using technology not yet invented. But it is being asked, and it will keep being asked. And someday, perhaps in a decade, perhaps in a century, the answer will begin to emerge. It will probably be stranger than any theory we currently have. It will probably require us to revise concepts we currently take for granted. It will almost certainly reveal that the universe is even more extraordinary, even more counterintuitive, even more astonishing than we currently imagine. Because that has been the pattern of discovery in physics for 400 years. Every time we have pushed our understanding to a new depth, the universe has been stranger, richer, and more beautiful than we expected. There is no reason to think that pattern will end when we reach the boundary of the Big Bang. If anything, everything we know suggests that what lies beyond it will be the strangest, richest, most beautiful thing we have ever encountered. We have spoken repeatedly about the Planck time as a kind of wall, a moment before which our current physics cannot describe what happened. But it's worth spending time on exactly what the Planck epoch is, what happens there, and why it represents such a fundamental barrier to understanding. The Planck epoch is defined as the period from the beginning of time, whatever that means, to approximately 10 to the negative 43 seconds after the Big Bang. This is the Planck time, named after the German physicist Max Planck, who first showed that certain combinations of fundamental constants of nature, the speed of light, Planck's constant from quantum mechanics, and Newton's gravitational constant, define natural units of length, time, mass, and energy. These Planck units set the scale at which quantum gravitational effects are expected to be overwhelming. To give you a sense of how extreme this is, the Large Hadron Collider at CERN, the most powerful particle accelerator ever built, accelerates protons to energies of about 14 trillion electron volts. 14 TeV. This is an extraordinary achievement that has revealed the Higgs boson and probed the structure of matter at the smallest scales ever explored in a laboratory. The Planck energy, the energy at which quantum gravity effects are expected to become dominant, is roughly 10 to the 19th giga-electron volts, or 10 billion giga-electron volts. That is about 1 quadrillion times more energetic than anything the LHC can produce. We are not going to build a particle accelerator that reaches the Planck scale, not in a century, not in a millennium, not ever, in any realistic engineering scenario. This means we cannot directly probe Planck-scale physics in the laboratory. We are forced to either reason theoretically, building mathematical models and hoping they're correct, or look for indirect imprints of Planck-scale physics in cosmological observations. The latter approach is genuinely promising, because the very early universe was at Planck-scale energies, and the fluctuations created then have been stretched by billions of years of cosmic expansion to scales we can observe in the CMB and in the large-scale structure of the universe. But here's the fundamental problem. At the Planck scale, quantum mechanics and gravity are both simultaneously important. Quantum mechanics governs the behavior of matter at tiny scales. It predicts the discrete energy levels of atoms, the probabilistic outcomes of measurements, the wave-particle duality of photons. General relativity governs the behavior of gravity and the structure of spacetime at large scales and high densities. These two theories are both extraordinarily successful in their respective domains, and they are fundamentally incompatible with each other in their current forms. The incompatibility is technical but important. In quantum mechanics, every physical quantity is described by a quantum state, a probability distribution over possible measurement outcomes. The evolution of quantum states is governed by linear equations, equations where superpositions of solutions are also solutions, and where different parts of the quantum state evolve independently. This linearity is crucial to quantum mechanics. It's what makes quantum interference possible, and interference is responsible for many of quantum mechanics' most distinctive predictions. General relativity, on the other hand, is a deeply nonlinear theory. The equations governing the curvature of spacetime are nonlinear partial differential equations, and the solutions do not superpose. Two different solutions cannot simply be added together to get a third valid solution. This nonlinearity is also crucial. It's what makes gravity self-interacting, what allows gravitational waves to carry energy, and what gives rise to phenomena like black holes. When you try to apply quantum mechanics to the gravitational field, to quantize gravity the way we've quantized electromagnetism, giving us quantum electrodynamics QED, and the other forces, the nonlinearity of general relativity creates mathematical catastrophes. The theory produces infinite answers for physical quantities that should be finite. Specifically, the graviton self-interaction, when computed in the same way as the photon self-interaction in QED, generates infinities that cannot be removed by the mathematical procedures, renormalization, that work for QED and the other quantum field theories. Quantum gravity, in this straightforward approach, is non-renormalizable. It is mathematically broken. This is the central technical reason why we don't have a theory of quantum gravity. It's not for lack of trying. Some of the best mathematical physicists of the 20th century worked on this problem. Feynman worked on it. DeWitt worked on it. Quantum gravity has been known to be a central unsolved problem since the 1930s, and despite enormous progress on the two leading candidate theories, string theory and loop quantum gravity, neither has produced a complete tested theory of quantum gravity. Both have made partial progress. Both have illuminated aspects of the problem. Neither has definitively solved it. Until it is solved, everything that happens at the Planck epoch is, at best, model-dependent speculation. We can write down equations, the Wheeler-DeWitt equation of quantum cosmology, the effective equations of loop quantum cosmology, the superstring action of string theory. But we cannot be confident that any of these equations correctly describes what actually happened. The Planck epoch is the domain where our ignorance is most complete and most fundamental, and here is the haunting part. The pre-Big Bang universe, whatever it was, connects to us through the Planck epoch. Whatever information about the pre-Big Bang state survives in our observable universe today had to survive the Planck epoch to get here. If the Planck epoch is as chaotic and physically extreme as we think, it may have thoroughly scrambled that information. The pre-Big Bang universe may have sent us a message, but the message may have been so thoroughly scrambled by passage through the Planck epoch that we can never read it in full. This is not quite the same as saying the pre-Big Bang universe is permanently unknowable. It's saying that our access to it is limited by the scrambling effect of the Planck epoch. Some information might have survived, specific imprints in the CMB spectrum, the gravitational wave background, the distribution of primordial black holes, but much information may have been irreversibly lost, not because it doesn't exist, but because it cannot be reconstructed from what we observe. Cosmologist Abhay Ashtekar, one of the founders of loop quantum gravity and loop quantum cosmology, has described this situation using the analogy of a scrambled egg. You can tell that it was once an egg. You might even be able to tell some things about the properties of the original egg. But you cannot reconstruct every detail of the egg's original structure from the scrambled version. The universe is similar. We can tell that there was something before the Big Bang, if our theories are right, and we might recover some properties of it from what we observe today, but a complete reconstruction of the pre-Big Bang state may be beyond reach. Understanding the structure of the Planck epoch, building a working theory of quantum gravity, remains the central task in fundamental theoretical physics. If and when that task is accomplished, the question of what came before the Big Bang will become answerable, in a much more precise and potentially testable way. Until then, we explore with the tools we have, knowing they are incomplete. One of the most profound questions that emerges from thinking about pre-Big Bang cosmology is a question that connects to black hole physics, quantum mechanics, and the foundations of thermodynamics. Does the universe preserve information about its past? And specifically, can information from before the Big Bang survive into our observable universe today? In classical physics, the answer is unambiguous. Classical physics is deterministic. The state of a physical system at any one time completely determines its state at all other times. Given the state of the universe at the Planck-epoch, classical physics would allow you to compute, in principle, every detail of the universe's subsequent evolution. And running the equations backward would allow you, in principle, to recover the complete state of the universe before the Planck epoch from its state afterward. Information is perfectly preserved in classical physics. Nothing is ever truly lost. In quantum mechanics, the situation is more subtle. The evolution of a closed quantum system is governed by the Schrödinger equation, which is unitary, meaning that it preserves all information in the quantum state. If you know the quantum state at one time, unitary evolution allows you to compute it at any other time, forward or backward. This is quantum information conservation. The total information in a closed quantum system cannot change. But here's the complication. The Big Bang, or the bounce, or whatever transition led to our universe, was not an ordinary physical process occurring in a static space-time. It was a process that involved the creation or transformation of space-time itself. General relativity allows for the creation of regions of space-time, new causal patches, new horizons, new topologies, and when space-time topology changes, it's not clear that quantum unitarity, quantum information conservation, continues to hold in its usual form. This is essentially a version of the black hole information paradox in a cosmological context. When matter falls into a black hole, the information about that matter is seemingly destroyed, lost behind the event horizon, and then lost forever when the black hole eventually evaporates, since Hawking radiation is thermal, carrying no information about what fell in. This would violate quantum unitarity. The resolution of the black hole information paradox, whether information is preserved and if so how, has been one of the central debates in theoretical physics for decades, and it's still not fully resolved, though progress has been made. In the cosmological context, the analogous question is, does information from the pre-Big Bang universe survive the transition to our universe? In loop quantum cosmology, the mathematical evolution of the quantum state through the bounce is deterministic and unitary. In the model, information is preserved through the bounce. This is actually one of the mathematically attractive features of LQC. It resolves the singularity and maintains quantum unitarity through the transition. But whether this mathematical feature of the model reflects reality depends on whether LQC is the correct theory, which we don't know. In eternal inflation, each bubble universe is, in a technical sense, causally disconnected from the others. Information does not flow between bubble universes in any direct way. The state of our bubble universe is determined by the quantum state at the moment of nucleation from the inflationary background, and the imprint of the broader inflationary context is encoded in the statistical properties of the resulting universe. The spectrum of fluctuations, the geometry, the values of fundamental constants in the settled vacuum state. But the detailed state of other bubble universes, or of the inflationary background before our bubble nucleated, is not encoded in our universe in any directly readable way. The conformal cyclic cosmology of Penrose is particularly interesting from an information perspective. Penrose proposes that specific types of information, specifically the gravitational wave signals from the final evaporation of supermassive black holes, can propagate through the conformal crossover from one aeon to the next. This is the origin of the Hawking points he predicts in the CMB. In Penrose's framework, some information makes it through, but most does not. The entropy of each aeon is reset at the crossover, and the detailed microscopic state of the previous aeon is not recoverable from the next one. The thermodynamic dimension of this question is also profound. Entropy, the measure of disorder or information content in a physical system, tends to increase over time in any system that evolves according to the second law of thermodynamics. In cosmological terms, the universe's entropy has been increasing since the Big Bang, and will continue to increase until the heat death of the universe, at which point entropy is at its maximum. A question that haunts cyclic models is, if entropy increases within each cycle, how does the next cycle begin with lower entropy? Where does the low entropy of the Big Bang come from? Different pre-Big Bang theories handle this differently. In loop quantum cosmology, the details depend on what the pre-bounce state looked like. If the pre-bounce universe was in a high entropy state, the bounce might not obviously produce a low entropy initial state for our universe, which is what we observe. In the ekiparotic cyclic model, Steinhardt and Turok propose that the entropy is reset at each brane collision, that the entropy from one cycle is diluted by the vast expansion of the cycle and is effectively negligible at the next collision. In Penrose's CCC, the conformal crossover is designed precisely to address this. The Weyl curvature, a measure of the structure and entropy of the gravitational field, is forced to be low at the beginning of each aeon, implementing a kind of entropy reset. The thermodynamic and information theoretic aspects of the pre-Big Bang question are not peripheral, they are central. The second law of thermodynamics, the inexorable increase of entropy, is one of the most fundamental and well-confirmed laws in all of physics. Any satisfactory account of what came before the Big Bang must explain why our universe began in such an extraordinarily low entropy state. The initial entropy of the observable universe was so low that the physicist Roger Penrose, long before he developed CCC, estimated the probability of it arising by chance from among all possible initial states at roughly 1 in 10 to the power of 10 to the power of 123. That is not a number. That is a number that makes other large numbers look infinitesimally small. The low initial entropy of the universe is one of the deepest and least understood features of our cosmos, and any theory of what came before must account for it. We cannot discuss pre-Big Bang cosmology, honestly, without addressing the fine-tuning problem and the anthropic principle, because they are intimately connected to questions about what kind of universe came before ours and why. The fine-tuning problem refers to the observation that the fundamental constants of nature, the strength of gravity, the charge of the electron, the mass of the proton, the cosmological constant, dark energy, the Higgs vacuum expectation value, and dozens of other parameters, appear to be exquisitely tuned to values that permit the existence of stars, planets, chemistry, and life. Even tiny changes in these values would produce a universe radically different from ours, one in which stars don't form, or atoms are unstable, or the universe collapses immediately after the Big Bang, or expands so quickly that no structure ever forms. The cosmological constant is the most extreme example, the dark energy driving the accelerated expansion of the universe has a value of about 10 to the negative 122 times the Planck density. Quantum field theory calculations, naive estimates of how big the vacuum energy should be, predict a value about 122 orders of magnitude larger. This is the worst prediction in the history of physics, a factor of 10 to the 122 between the predicted and observed values. The cosmological constant is incredibly, inexplicably small. And this smallness is crucial for our existence. If the cosmological constant were as large as quantum field theory naively predicts, the universe would have expanded so rapidly after the Big Bang that no galaxies, no stars, no planets, and no observers would ever have formed. We exist, it seems, because the cosmological constant is tuned to an extraordinarily precise small value. What explains this fine-tuning? There are essentially 3 possible types of answers. The first is that the fine-tuning is not actually as extreme as it appears, that some deeper theory will show why these constants must have these values, eliminating the apparent fine-tuning by deriving the values from first principles. This has been the hope of unified theories throughout the 20th century. String theory and M theory were initially hoped to pick out a unique vacuum with the right physical constants. But as the string landscape was explored in the late 20th and early 21st centuries, it became clear that string theory permits an enormous number of possible vacua with different constants, rather than a unique one. This hope has not been realized, and most physicists no longer expect a single unique vacuum from string theory. The second is the multiverse explanation. There are enormously many universes, each with different values of the fundamental constants, and we necessarily find ourselves in one that has values permitting our existence. This is the anthropic selection effect. Out of all the possible universes, we can only observe the ones that permit observers, and those happen to be the ones with finely tuned constants. The multiverse, whether from eternal inflation and the string landscape, or from the ekpyrotic cycle, or from some other mechanism, provides the ensemble of universes from which anthropic selection can operate. This is intellectually uncomfortable for many physicists, because it seems to abandon the project of explaining why things are the way they are in favour of saying, they had to be this way for us to notice them. It feels like a non-explanation. But defenders of the anthropic principle point out that we use this type of reasoning elsewhere without discomfort. We don't ask why the Earth is at just the right distance from the Sun to permit liquid water, because we understand that life can only arise on planets with liquid water, and so observers will always find themselves on such planets. The anthropic principle applied cosmologically is structurally the same reasoning, just applied to the constants of nature. The third possibility is design, that the fine-tuning reflects the intentional action of an intelligence that chose the constants to permit life. This is the position of many religious believers and some philosophers. It is not a scientific hypothesis in the testable sense, and most working physicists don't treat it as such, but it is a coherent philosophical position and deserves honest acknowledgement. The fine-tuning problem connects directly to pre-Big Bang cosmology, because several of the pre-Big Bang theories provide natural mechanisms for the anthropic explanation. Eternal inflation and the string landscape provide the ensemble of universes needed for anthropic selection. The cyclic model, with its potentially infinite series of cycles, also provides an ensemble, not in space, like bubble universes, but in time. If each cycle produces a universe with different physical constants, depending on how the extra dimensions settle after each brane collision, and if intelligent life can only arise in cycles with appropriate constants, then we would naturally find ourselves in such a cycle. Loop quantum cosmology, in its cyclic version, could potentially also generate an ensemble of universes through repeated bounces, each with different properties. And conformal cyclic cosmology potentially generates an infinite sequence of aeons, though Penrose's framework doesn't obviously produce different physical constants in each aeon. It tends to produce the same constants throughout. The fine-tuning problem is not solved by any of these theories, but several of them provide the structural ingredients that a solution to fine-tuning would require. Specifically, a large ensemble of universes with varying properties from which anthropic selection can operate. Whether that's the right solution remains deeply contested. One of the most striking features of modern cosmology is how much of the universe we don't understand. Dark matter, the mysterious substance that makes up 27% of the total energy content of the universe, has been inferred from its gravitational effects since the 1930s, but has never been directly detected. Dark energy, the even more mysterious form of energy that makes up 68% of the total energy and is driving the accelerating expansion of the universe, was discovered only in 1998 and remains completely unexplained theoretically. Could these mysterious components of our universe have their origins in the pre-Big Bang era? For dark matter, one tantalizing possibility has emerged from the study of bouncing cosmology. A recent study published in the Journal of Cosmology and Astroparticle Physics in 2024 explored a scenario in which dark matter consists of primordial black holes. Black holes formed not from collapsing stars but from density fluctuations in the very early universe. In the context of a bouncing cosmology, these density fluctuations could have been produced during the final contraction phase of the universe before the Big Bang bounce. If the contracting phase produced density fluctuations at the right amplitude and scale, some of those fluctuations might have been large enough to collapse directly into black holes during the contraction, and those black holes would have survived the bounce and populated our universe as dark matter. This is a remarkable idea. The dark matter permeating every galaxy you've ever seen might be the remnants of the universe that existed before our own Big Bang. This is genuinely speculative, but it illustrates the kind of connection that can be made between pre-Big Bang theories and observable quantities. If dark matter turns out to be primordial black holes, and if the mass spectrum of those black holes matches the predictions of a specific bouncing cosmology model, that would be extraordinary evidence for a pre-Big Bang era. Dark energy presents a different kind of connection to pre-Big Bang physics. The cosmological constant, the simplest explanation for dark energy, is the energy density of the quantum vacuum. In quantum field theory, the vacuum is filled with virtual particle fluctuations, and these fluctuations contribute to vacuum energy. The problem is that the naive estimate of this vacuum energy is about 10 to the 122 times larger than the observed value of the cosmological constant. Some mechanism must suppress the vacuum energy by this enormous factor. Some pre-Big Bang theories offer potential insights into this. In the string landscape, different bubble universes have different values of the cosmological constant, determined by how the extra dimensions are compactified. Anthropic selection could explain why we observe a small positive cosmological constant. Only universes with cosmological constants small enough to permit structure formation would host observers. But this doesn't explain the mechanism of suppression. It just says we shouldn't be surprised to observe a small value. The actual physical mechanism that sets the cosmological constant at its observed value remains unknown. In some cyclic models, the cosmological constant evolves from cycle to cycle. Steinhardt and Turok's cyclic model was partly motivated by the desire to explain the cosmological constant through a dynamical mechanism rather than anthropic selection. The constant could drift towards smaller values over many cycles, and we find ourselves in a cycle where it's small enough for structure to form. These connections between dark matter, dark energy, and pre-Big Bang physics are not fully worked out. They represent the frontier of current research, areas where the questions are sharper than the answers. But they demonstrate that the question of what came before the Big Bang is not purely philosophical or academic. It connects to some of the most pressing, concrete, observationally motivated questions in modern cosmology. There is one more dimension of this question that deserves mention, because it's genuinely thought-provoking even if it remains speculative. The question of whether consciousness or observation plays any fundamental role in the structure of the universe and its origins. This might sound like it's heading toward mysticism, and I want to be clear that what I'm describing is a serious, if contested, area of theoretical physics. It originates with the quantum measurement problem, the deep conceptual difficulty at the heart of quantum mechanics. Quantum mechanics describes the behavior of particles as probability waves, quantum states that encode the probability of various measurement outcomes. Before a measurement, a particle can be in a superposition of multiple states simultaneously. When a measurement is made, the quantum state collapses to a definite outcome. But what constitutes a measurement? What is it about the act of observation that causes the quantum state to collapse? Does the universe remain in superposition until observed? By whom? Does the observer have to be conscious? Most physicists today avoid these questions by adopting the shut up and calculate approach, using the mathematical formalism of quantum mechanics to make predictions without worrying about interpretational questions. Quantum mechanics makes extraordinarily accurate predictions. The Copenhagen interpretation, the many worlds interpretation, the de Broglie-Bohm pilot wave theory, and other interpretations all make the same experimental predictions, but give different answers to the interpretational questions. Most physicists work in a particular interpretation by default without feeling the need to resolve which one is really true. But in quantum cosmology, in the quantum mechanics of the universe as a whole, the measurement problem becomes unavoidable. Who measures the universe? The universe, by definition, contains everything. There is no external observer to collapse its quantum state. Hawking and Hartle's no-boundary proposal addresses this by treating the universe's quantum state as a specific mathematical object, the no-boundary wave function, and computing quantities from it directly without invoking collapse. But the interpretation of this wave function remains deeply contested. Physicist John Wheeler, one of the great conceptual thinkers of 20th century physics, proposed what he called the participatory universe. Wheeler's idea was that the universe, at the quantum level, does not have a definite structure until it is observed, and that observations, acts of participation, give the universe its properties retroactively. He famously spoke of delayed choice, experiments, where the decision about how to observe a photon can determine after the fact which path it took. Wheeler extended this idea to cosmological scales, suggesting that observations we make today might retroactively determine the path the universe took 13.8 billion years ago. Whether Wheeler was right is debated. Mainstream physicists tend to be skeptical of any interpretation that makes consciousness special in the laws of physics. But the measurement problem in quantum cosmology remains genuinely unresolved, and the question of what role observation plays in determining the history of the universe, including any pre-Big Bang era, is not one that can be dismissed as having an obvious answer. We have covered a vast amount of ground tonight. Let me take a moment to reflect on the shape of what we've explored, because there's a pattern in it worth naming. Every theory of the pre-Big Bang universe that we've discussed has a certain structure. It proposes a state or a process that preceded our observable universe. It provides a mechanism by which that prior state gave rise to the hot Big Bang that started our cosmic history. And it makes predictions, more or less specific, more or less testable, about observable properties of our universe that encode information about what came before. The theories differ in what they propose came before, but they all share something. They refuse to accept the singularity as the end of the story. They all say, in different ways, the Big Bang was not the absolute beginning, something preceded it, and they all use the available mathematics, quantum mechanics, general relativity, string theory, conformal geometry, to try to describe that something. This refusal to accept the singularity as an absolute beginning is not wishful thinking. It's not the physicist's version of "I don't want there to be an end to the story." It's a well-motivated physical intuition. Singularities in physics are almost always signs that a theory has been pushed beyond its domain. When Newton's theory of gravity predicted an infinite force between two-point masses at zero distance, it was telling us that the theory broke down at short distances, which quantum mechanics confirmed. When early quantum field theory predicted infinite masses for elementary particles, it was telling us that naive perturbation theory broke down, which renormalization addressed. When general relativity predicts a singularity at the Big Bang, it is almost certainly telling us that general relativity breaks down there, and that a quantum theory of gravity would resolve the singularity. The singularity is a symptom of incomplete theory, not a physical reality. And where the singularity resolves, a pre-Big Bang universe may be found. The history of science supports this attitude. For centuries people assumed that the Earth was special, that the solar system was all there was, that the Milky Way was the entire universe. Each expansion of scale has revealed a more vast, more complex, more surprising cosmos. The visible universe is 93 billion light-years across, containing perhaps 2 trillion galaxies. The observable universe is just a tiny patch of all that exists, and all of that might be just one bubble in an eternal inflationary sea, or one aeon in a cyclic sequence, or one brane among many in a higher dimensional bulk. The expansion of what we call the universe has no obvious stopping point. Each veil we lift reveals another veil behind it. What's behind the Big Bang might be revealed to be not a beginning but a transition, from one vast, complex cosmic epoch to another, stretching back farther than we can currently imagine, and forward further still. If you could, right now, ask one question about the pre-Big Bang universe and receive a definitive, accurate answer, what would it be? Would you want to know if there was a before at all? If time began with the Big Bang, or if it extends back further? Would you want to know how many universes there are? Would you want to know the physics of the Planck epoch, the true quantum theory of gravity that our century has not yet produced? Would you want to know if consciousness plays any role in the structure of physical reality at the deepest level? Would you want to know if the fine-tuning of our universe's constants is the result of random chance in an enormous multiverse, or design, or some deep mathematical necessity we haven't yet understood? These are all versions of the same question, really. They all ask, is there more to reality than what we can currently see and measure and calculate? And the honest answer, the answer that modern physics gives, is almost certainly yes. There is almost certainly more to the universe than the 13.8 billion light-years of cosmic history we can trace. The question is what that more is, and whether we will ever fully understand it. The greatest scientists in history were comfortable with profound uncertainty. Einstein spent the last decades of his life searching for a unified field theory that eluded him. Feynman was famous for saying he could live with not knowing things, and that it was better to say, "I don't know," than to give a bad answer. The physicists who spend their careers on quantum gravity and pre-Big Bang cosmology know better than anyone how much we don't know. And that knowledge of ignorance, that precise, detailed understanding of where our understanding ends, is itself a form of knowledge. It is the most advanced form, knowing exactly what you don't know. We don't know what was here before the Big Bang. We know the question, we know the landscape of possible answers, we know what we would need to observe or calculate to distinguish between them, and we know that the answer, when it comes, will almost certainly be stranger and more beautiful than anything we currently imagine. That is where we are, right at the edge, looking out, The universe is vast and beautiful and stranger than anything we've fully mapped yet, and the territory beyond the Big Bang, whatever lies there, is the most unmapped territory that human inquiry has ever faced. We are just beginning to understand what it would take to truly explore it. Thank you for joining us on this journey. If this exploration moved you, challenged you, or left you staring at the ceiling at 2 a.m. thinking about what before time began could possibly mean, please hit the like button and subscribe to the Cosmic Pup. Every new subscriber is another curious mind joining this conversation, and the conversation, like the universe itself, is only just getting started. Stay curious. The stars are waiting, and so, apparently, is whatever came before them. See you later, guys.